And welcome to our next installment of Chem Honors Online, in which we're going to discuss something called the hydrolysis of salts. So, we defined salts recently as ionic compounds that don't contain H plus or OH minus. We have a slightly modified definition here for you. An ionic substance that does not contain oxide or hydroxide. Now notice there's no mention of hydrogen because HX, all acids are covalent, so it's not an ionic compound. And so essentially we should be calling them salts ionic compounds without O2 minus or hydroxide. And an alternate definition of a salt, another way of looking at it really, is that it's a substance that's formed when an acid reacts with the base. Just like we saw the other day when we had a neutralization reaction. We have, for example, hydrochloric acid and potassium hydroxide. And these two things form in a neutralization reaction. We have a double replacement where the H plus goes with the OH minus to make water, and the chloride goes with the potassium to make KCl. And KCl is our salt, and that aqueous solution of salt, because it is aqueous, contains the dissociated potassium chloride. So the potassium and chloride, we saw this in the net ionic equation too. Those two became the spectator ions. These two things are going to stay in solution. Now, here's the thing. These guys in solution might, and this is where the big trick is going to be coming to understand when, might react with water. And that reacting with water, that's the hydrolysis that we're talking about. So hydrolysis of salts is a process by which one of those ions, or both of them, but usually it's only one, reacts with water. And when it does, this is the cool thing, it reacts with water to form an acid or a base, because that ion itself is, the ion is, I'm not going to write it here, the ion is acidic or basic. Now, in order to do that, there's a couple of ground rules. The ion, that's what I wanted to write here, the ion must be between hydronium ion and hydroxide ion on chart G, or have a Ka or Kb between 1 and 1 times 10 to the minus 14. We'll usually see those ranges. And when that happens, then we're going to be able to get hydrolysis. All right. So to determine if we have an acidic or basic solution, you're going to look to see if one of the ions is an acid or base. And by that I mean, is it on chart G, is it on the left side, it's an acid, on the right side, it's a base? Or do I give you a Ka or a Kb, or somehow you know that I told you that it's a weak acid or a weak base? So it always has to be the conjugate of a weak acid or a weak base, as we will discuss a little bit below. So strong acids and strong bases react 100% to the right. We've seen these before. So their conjugate bases and acids don't react. In other words, as I showed you on previous answer sheet, I think I did this in class, that chloride does not react with hydronium ion, doesn't react with water to form HCl, because that HCl will then just come apart. So their conjugate bases and acids do not react. So you've got to know your strong acids and your strong bases. Strong acids, again, at the top of chart G. Strong bases either at the bottom of chart G, or the hydroxides of the alkali metals and the 3 alkaline metals that form that B. So the conjugate bases of strong acids and the conjugate acids of strong bases do not undergo hydrolysis. Instead, they would form what we call a neutral solution. So KCl up above, because the potassium comes from a strong base, The chloride comes from a strong acid. They're the conjugates of strong acid, strong base. Potassium chloride would actually be a neutral solution. Now, if we were actually going to be doing this in class, I would show you, and I don't think I looked for it. I couldn't find, I don't think I've got pictures of the results of this. A demo in which I have these 5 salts dissolved in water along with some universal indicator. But I'm just going to give you the results, and you know what, maybe I'll use some color coding to do so. Sodium carbonate. Sodium carbonate, ionic compound, splits into sodium and carbonate, and the color in universal indicator would be violet. The pH would be a very strong base, 11, and the ions that are in that salt are sodium plus, we don't need to put 2 of them, we just need to know what's there, and CO3, 2 minus. Now, let's go over to chart G. And chart G, sodium, first of all, sodium is a conjugate acid, technically, of a very strong base. It's not going to hydrolyze. But carbonate is going to hydrolyze. Carbonate is right down here. Oh, I need a pen. And notice what side of the reaction carbonate is on. Carbonate is a base. So that means it's going to hydrolyze. It's going to react with water as a base. So let's go back to our worksheet and let's write that reaction of carbonate in water. So the reaction is going to take CO3, 2 minus. We're not going to be concerned, let me write that Q a little bit better, at all with the sodium. The sodium, in fact, as we said above, the sodium does not undergo hydrolysis. They cannot take OH minus off of water. What would it make? It would make sodium hydroxide and hydrogen ion. And sodium hydroxide and hydrogen ion, the hydroxide and the hydrogen ion are just going to react to form sodium plus and H2O. So you'll just go that direction and you'll never make anything else. But carbonate is going to react with water. Remember, water is everywhere. Water is all over the place. So we have carbonate there, we got water there. Now the carbonate is the base, so it's going to take an OH, and let's see, let's use light blue because that's not going to come. It's going to take not OH, it's going to take an H off of the H2O, and it's going to form the hydrogen carbonate, HCO3 minus, and leave behind OH minus. And that OH minus, that's the source of the base. And when I say the equations to support the pH value, you should be looking for either hydroxide here or hydronium ion to correspond to the pH. Okay, so far? Let's take a look at sodium acetate. I don't think this is going to be the right color, but it's going to be close enough. I don't think I have this color. Sodium acetate splits between the sodium and the acetate. By now, you should recognize where to split those ionic compounds. Color in universal indicator is going to be kind of a teal color, kind of bluish, and it has a slightly lower pH of 9. Now, that pH of 9 still means it's basic. Again, we've got sodium here. We also have the acetate ion, CH3COO minus is one way to write it. As we saw before, sodium is not going to ionize, but if we go back to chart G, we're going to find acetate, and we will find acetate near the top of the weak acids. Here's acetic acid. There's our acetate. It's on the right side, so acetate is going to hydrolyze as a base. Let's go back to our sheet so we can write CH3 COO minus plus H2O. Again, it got that water there. We're going to take that proton off. I'm not going to draw the arrow this time because it's going to get too sloppy. And we're going to reform. Notice we're forming CH3COOH. We're making the weak acid. Now, this weak acid, because it's a weak acid, doesn't dissociate 100%. It stays together, so we write it together, and we get the OH minus that's left over. And there's the hydroxide that gives us our basic solution. Okay, moving right along. Sodium chloride. So we've got sodium chloride. They're going to split at the sodium and the chloride. And universal indicator is going to give us a green solution. And that indicates a pH of 7 for a neutral solution. So what do we have? We have sodium plus, we have chloride minus. Now, chloride, you know now that chloride is the conjugate base of a very strong acid. But let's go to chart G just to show you how this works. Chloride is up here at the top. Chloride is the conjugate base, but notice this reaction only goes in one direction. This reaction does not return, does not go in the reverse direction. So this chloride, because the Ka of HCl is very large, the chloride itself does not hydrolyze. It's also a neutral ion, and so you would write none. Oh, I need my pen. You would write none. And we can just write in here, just to be sure, both ions are neutral. Okay, ammonium chloride. Ammonium chloride, let's see what goes on here. Ammonium, now first of all, we got all nonmetals there, but you have to recognize, you need to recognize that ammonium ion. And we're going to split at the ammonium and the chloride. And as I've indicated with my pen color, this would give us an orange solution in universal indicator, and it would give us a pH of about 5. The ions that are there, we've got ammonium, NH4+, and we've got chloride. Now, we've already discussed chloride. Let's go to chart G and look at ammonium. Let's get to my orange pen. And let's scroll down towards the bottom. And we can find ammonium in that region. Again, we want to look between the hydronium ion and the hydroxide ion. So it's got to be in here somewhere. And sure enough, there's our ammonium. Now look at what side it's on. The ammonium is going to hydrolyze as an acid. I hope this is making sense to you. By looking at this chart, we can see. Now, we'll have one example in our homework in which it's not going, or a couple of examples in which it's not exactly that way. But I'm going to give you whether it's a strong acid or a weak acid or a weak base. Okay, so back to here. The ion that hydrolyzes is going to be the ammonium. So we're going to write N, oops, a little delay there. NH4+. Again, the chloride is going to act as a spectator ion. It's not going to get involved at all, so don't worry about it. Now, when we put the ammonium together with water, the ammonium is the acid and the water is the base, and so we're going to take a proton off of the ammonium to make ammonia. Now, ammonia is aqueous. It forms hydrogen bonds with water, so it's polar enough, and it does dissolve in water. And we're going to make some H3O+. And there's the hydronium ion that supports the pH of 5. Finally, potassium nitrate. I don't know if I'm going to give it away here. Potassium and nitrate split at the potassium and the nitrate. This is also going to be green with a pH of 7. There's our potassium, K+. K+, it's an alkali metal. It's going to do the same thing. It does not hydrolyze. Nitrate. Nitrate, if we go to chart G, nitrate is up at the top again. Nitrate is the conjugate base of a strong acid. NO3, there it is, right below the chloride. So because it's up here, anything up here, do not hydrolyze. Okay, let's go down to the bottom as well. Anything down here, do not hydrolyze. I realize it sounds like I was saying bad grammar. I'm telling you not to do not hydrolyze them, not that they do not hydrolyze, but don't hydrolyze them. All right, so those guys aren't going to hydrolyze. So ammonia, this thing isn't going to hydrolyze. Hydroxide isn't going to hydrolyze. Now, that's in the forward direction. These guys, that reaction does take place. That's not a hydrolysis. That reaction would take place. All right, so let's finish that off. No reaction. So we can say NR for no reaction. Both ions are neutral. All right, so this is how we get different acidities and basicities of different salts. And this has an effect on the pH at the equivalence point when you titrate. So if you go back up above, you can see that that first reaction I showed you today was the neutralization of hydrochloric acid with potassium hydroxide. It does the same thing, looks exactly the same as with sodium hydroxide. That's a titration. And the pH, when you have that titration done, is going to be 7. That is going to be a true neutralization. So let's look at HBr, a strong acid, and sodium hydroxide, a strong base, and see how this works. When we form our reaction, we're going to make H2O, and we're going to make sodium bromide aqueous. Okay, now, at exactly the equivalence point, remember all of the acid and base are exactly consumed. So now the only thing we've got in the solution is the water and the salt that we just made. There's nothing else there, right? There's no excess sodium hydroxide. There's no excess HBr. What ions are there in the salt? Split it apart. Like we're doing a net ionic equation, we have sodium and we have bromide. Now, as we said before, sodium does not hydrolyze. Let's go to chart G because we haven't seen this one yet. I just want to prove to you that it does in fact work. Where's bromide? There's bromide way at the top in that do not hydrolyze zone. So the bromide, also doesn't hydrolyze. So again, neither hydrolyze, neither ion hydrolyzes. So at the equivalence point, the pH is equal to 7, and we have a neutral solution. All right, we've got the conjugates of a strong, conjugate of a weak. Conjugate of, both of them conjugate of strong, I'm sorry. And so neither one is going to hydrolyze. And so we'll get the pH of 7. By the way, this can also happen if you just inadvertently happen to have a weak acid and a weak base that have exactly the same ionization constant. We're not going to deal with that, though, because that gets a little more confusing. Again, a future class will help you deal with that if you're interested. Now, suppose we have a weak acid and a strong base. So in this weak acid and strong base, we're going to have acetic acid and sodium hydroxide. Now, a mnemonic, a way of remembering this is that the strong one is going to win. And we're going to end up having a basic solution at the equivalence point. All right, so this is a mnemonico. This isn't a reason. The reason is going to come from what ions there are in solution. So when we do our neutralization reaction, we're going to take the H and the OH, we're going to put those together to make water. You can write it HOH if you want. And we're going to make sodium acetates, NaCH3COO minus. Now, not a minus, there's no minus there because it's together in the compound. Now, we did see this up above, but this is how it's going to help us to understand what's going on here. Again, at the equivalence point, the acid and base are consumed. The only thing we have is the water and the salt. Water is water. what's the salt doing? The ions are sodium and acetate. And so that acetate undergoes hydrolysis because, as we saw before, that acetate is in that region between hydroxide and hydronium. And I should actually be writing these as equilibria. No, let's go back up to the top and rewrite those as equilibria. These are actually equilibrium reactions. Only when they hydrolyze, though. Only when they hydrolyze. So we can make those equilibrium reactions. Now let's come back down. And what do we make? We make our acetic acid. Now, the reason I wanted to emphasize that this is an equilibrium is that the K, this is a base, the Kb is really, really small. The Kb is less than 1. So this doesn't happen very far to the right. So you don't make a lot of acetic acid. And you also don't make a lot of hydroxide, so you don't have a very strongly basic solution. In this case, you notice that the pH for this particular reaction is 8.72, which is just under 9, which is that was the pH that we saw, and to the best ability for us to measure pH using pH strips and using indicator. 8.7 and 9 are basically the same, and so we have a basic solution because the acetate hydrolyzes as a weak base. And on chart G, you will notice that acetate is on the base side. It's between hydroxide and hydronium ion, and so it has everything you need to hydrolyze as a weak base. All right, let's finish it up. Let's look at the titration of a strong acid and a weak base. In this case, we're going to have the acid in the flask, and the base is going to be in the burette, and we're going to make it HCl and ammonia. Now, this is a little trickier because this looks like a Bronsted acid base. The thing is, because this is strong, because the HCl is strong, this reaction proceeds to the right. There's no equilibrium, and what's going to happen? You are going to take the H from the HCl and give it to the ammonia, and what you're going to make is NH4 plus. You're going to make the ammonium ion. You're making ammonium chloride, but the ammonium chloride stays apart in solution. Again, we've got water and salt as the only two things in solution, and we've got the ammonium, NH4 plus. We got the chloride, Cl minus, and this looks an awful lot like what we saw up above. The ion that undergoes hydrolysis is the ammonium, NH4 plus, and it can react with the water that's present. Again, in equilibrium, and we're going to give up, but again, this is an acid, but the Ka is less than 1. It's a lot smaller than 1. We're going to make the ammonia again, and we're going to make some H3O plus. There's the acid that we're looking for, and that gives us I should have written this in red. I'm not going to go back and do it though. And actually not red, probably orange. So this is going to give us a pH, that pH below 7, it looks like it's about a 5, which is what we saw up above. And so this is going to be an acidic solution. And so the equivalence point is going to be acidic. So this is always going to be the case when you have these things, different strengths, acid and base. Notice, again, mnemonically, the strong acid made an acidic solution. However, that's not the reason. It's because the ammonium is a weak acid. And when it works in water, we have a Ka expression. When it dissolves in water, we have that Ka that describes the formation of the hydronium ion. All right. Be on the lookout for unusual situations on the homework. There's one ion that if you're not careful about, you're going to come up with the wrong answer. Make sure that you followed all the guidelines I've given you. And like I said, there's going to be at least one one base that is going to not be on chart G. But I will tell you that it's a weak base, and so watch out for that one. All right. Do well, and I will see you next time in class.